Welcome to Leviverse. Hi, I'm M. Today, we will learn an important topic in physics called kinematics. If you are learning kinematics for the first time, you need to build a strong foundation to understand it properly. Remember one thing, what you will learn today was not developed in a single night or a few days. These ideas have evolved over several centuries. Today, we study this topic as a refined result of the work of countless individuals. Although a lot of information is available on the internet, not all of it is necessary right now. That is why we focus on a clear and concise summary. I will provide all the essential information you need to know. Now, let's come to the main question. What is kinematics, and why is it important? If you understand how kinematics evolved, you will appreciate the beauty of physics, and at the same time, it will help build the foundation of your thinking. Today, we will learn kinematics through a real-life problem, the cannonball problem. I'm not using a random example. It's a real-life example that was used in warfare to break walls. We will discuss the history of cannonballs another day. Let's come to the topic. Imagine a cannon firing a ball toward a castle to break its wall. Now, consider another example, a car moving along a road from point A to point B. When cannons became important in warfare around the 15th to 17th centuries, armies faced a practical question: at what angle and speed should we fire a cannonball to hit a target? When we try to solve this problem, we encounter several questions. How far should we place the cannon from the target? How does velocity change due to gravity, and what is the shape of the trajectory path? On the other hand, in real life, the distance between 2 points is not always a straight line. For example, roads often contain obstacles, so they are not always straight. However, we may want to measure how much distance is covered within a certain time. To solve such real-life problems, we define certain quantities that help us measure motion, such as velocity, distance, and time. One important thing to remember is that direction is sometimes necessary. We will explore this later. So, we focus on the following quantities. Here, we will explore these quantities and understand each of them clearly. So, in simple terms, kinematics describes how objects move, not why they move. Now, let's define it. The branch of mechanics that studies motion of objects without considering the forces that cause the motion. You might ask, when do we consider forces? We study forces in another chapter called kinetics, where we try to understand the reasons behind motion. To fully understand the above quantities, we need proper knowledge of the reference frame. Take a real-life scenario. This is the story of two men. One is sitting inside a train, and the other is standing on the platform. Imagine a ball moving up and down inside a moving train. Do these two men observe the same path of the ball? What do you think? The answer is very simple: they do not see the same path. The two men observe two different paths. Man A, who is sitting inside the train, sees an up and down motion, a straight line motion. But man B, who is standing on the platform, sees a parabolic path. You might ask what a parabolic path is and why the ball follows that path instead of a semicircular one. We will discuss these topics another day. For now, remember that a parabolic shape is a specific type of curve. We care about it because nature behaves in this way. When you throw a ball into the air, it follows the same type of path every time. We call this path a parabolic path. Now, let's return to the main topic. Here, both men see different paths, so who is observing is important for calculations. This is where the concept of a reference frame comes from. When we perform theoretical calculations, we use the xy plane in 2 dimensions, which called a coordinate system. This is a theoretical representation, in other words, a pen and paper representation. The interesting part is that we build these concepts in such a logical way that they are useful in real life. So we can say a reference frame is a coordinate system, along with a clock, used to measure the position, motion, and time of events. In simple terms, it is the point of view from which an observer describes physical phenomena. And why important, motion depends on the observer. The same object can be at rest or in motion in different frames. Position simply refers to the location of an object with respect to a coordinate system. Here, we use a coordinate system as a reference frame. Imagine an object as a dot in space. If we don't know an object's position, we can't determine where it is, and without that information, we're unable to perform operations like measuring distance, or how far the object is from a reference point, whether it is moving or at rest. Or it may move in a circular path. Here you can say that the object is moving because we observe it relative to the screen, which is at rest. So, we introduce a coordinate system. Now, let us place the point in a coordinate system. Now we know where the point is located. We can also determine whether it is moving or at rest. We represent the position of an object in a coordinate system with a vector. We will understand this in greater detail in later videos. For now, just remember that this is how position is represented. If the position of the object changes, we represent the new position in this way. To summarize, position is described using coordinates relative to an origin. Now, let's move on to the next topic, distance and displacement. Let's return to the cannonball problem. If you want to fire a cannonball at a castle, you need to know how far the cannon is from the castle. So, distance plays an important role. Now, suppose we want to travel from point A to point B. In theory, you could go in a straight line. Roads are not always straight in real life. So, here again, distance becomes important. When you analyze real-life situations, sometimes both distance and direction matter. Think about the cannonball example. The straight line distance is important, and direction is also crucial. However, when traveling from point A to point B by road, the straight line distance does not matter as much. To deal with such real-life situations, we define 2 different quantities, distance and displacement. Distance is the total length of the path traveled by an object. On the other hand, displacement is the shortest straight-line distance between the initial and final positions. Distance is a scalar quantity, it has magnitude only. Displacement is vector, it has both magnitude and direction. Distance can only be positive or zero. Displacement can be positive, negative, or zero. Distance depends on the actual path taken. Displacement is independent of the path and depends only on endpoints. Here, two questions arise: how can displacement be negative, and how is it path independent? To understand this, we first need to recall the coordinate system. Suppose point A represents an object located at -3, -2 in the coordinate system, and point B represents an object located at 3, 2 in the coordinate system. Now, if a car moves toward point A, we consider its velocity to be negative. Now, take another path from point A to point B. Here, distance is equal to the actual path traveled. But displacement is equal to the shortest path, which is the straight line path. Now take another example, where the idea of path dependence becomes clearer. In this scenario, displacement is zero. You may ask, why is it zero? The answer is very simple. If an object starts its journey from a point and returns to the same point, its displacement becomes zero because the initial and final positions are the same. Now, after fully understanding distance and displacement, we move to the next topic: speed and velocity. In our daily lives, we encounter many situations related to speed and velocity. Let us consider two types of roads. One is a winding road, and a car is moving on this road. And the other is a straight road. In both cases, we can see that the position of the car is changing. So speed is defined as the rate of change of distance with respect to time. Its unit is meters per second or m/s. Here, we do not consider direction, only the numerical value matters. But here, one question arises: what happens if we consider direction? In the case of a curved road, the direction changes many times. On the other hand, if the road is straight, the direction remains unchanged. This leads us to velocity. Velocity is defined as the rate of change of displacement with respect to time, and its unit is also meters per second. As mentioned earlier, we encounter many real-life examples of speed and velocity. However, it is important to understand that these concepts are deeply connected to the fundamental structure of the universe. When we study how the universe works, velocity appears again and again, so it is important to stay focused on this concept. To summarize, distance has no direction, and speed is simply the change of distance with respect to time. Therefore, speed has no direction, it only has magnitude. In contrast, velocity is the change of displacement with respect to time. Since displacement includes direction, velocity has both magnitude and direction. You might ask, why should we care about direction? The answer is simple: the laws of nature depend on direction. If the direction changes, the outcome of a physical phenomenon can change completely. You will understand this more deeply when you study vector addition, but for now, just keep it in mind. Now, let us discuss some important ideas: uniform speed and uniform velocity. Imagine a ball moving in circular motion. The ball may have uniform speed, but it does not have uniform velocity. Why? Because its direction changes at every moment. At each point, the tangent to the circle represents the direction of motion. Since the direction changes continuously, the velocity also changes continuously. Whenever velocity changes with respect to time, we define it as acceleration. This example is very important. In fact, one of the drawbacks of the Rutherford model of atomic structure comes from this idea: a changing velocity produces electromagnetic radiation. So, what is acceleration? Acceleration is the rate of change of velocity with respect to time. This change can be in magnitude, direction, or both. Imagine that a cannon fires a ball. It travels along a curved path. Gravity continuously reduces the upward velocity of the ball. At the highest point, the vertical velocity becomes zero, but the ball continues moving forward due to its horizontal velocity. After this point, the ball begins to fall downward, and its vertical speed increases in the downward direction. Importantly, gravity provides a constant downward acceleration throughout the entire motion, even at the highest point, where the vertical velocity is zero. This is a key idea in physics. Velocity can be zero at an instant, but acceleration does not have to be zero at that point. One important thing to remember is that uniform velocity and acceleration are fundamental concepts. Later, you will learn that the laws of physics can appear different depending on the observer, whether they are in a frame moving with uniform velocity or in an accelerating frame. For now, there is no need to worry about this, just keep it in mind. Coming back to acceleration, if acceleration is the change of velocity with respect to time, what is its unit? Acceleration is the change of velocity with respect to time. And velocity is measured in meters per second. V equal m by s, where m equals meter and s equals second. So, we get A equals m by s square. You might also ask, why do we not usually consider the change of acceleration with respect to time? You may already guess the answer. Although such a concept exists, called higher-order motion, it has limited practical application at this stage, so we do not focus on it right now. Now we are finally ready to face the challenge of the cannonball. At what angle and with what speed should we fire it to hit the target? We will complete this calculation in the next video. See you soon.